In this video, I'm going to explain how to solve the practical traveling salesman problem for any graph. The problem states that a salesman starts at one vertex. He must travel to all of the other vertices in the graph and return back to where he started. How should he do this in the most efficient way possible? I'm going to start by constructing my own custom graph. Now that my graph has been constructed, it's time to complete the algorithm. So the first step is to make sure that for all the direct edges, the weight of the edge is the minimum possible weight. That looks like it's already the case. The next step is to turn this into a complete graph by ensuring that between every pair of vertices, there is a direct edge between those vertices. For the weights, I'm going to assign the smallest possible weight that it takes to get between those vertices. So between A and B, the only way is to go this edge weight 16 plus 15 for a minimum weight of 31. A is connected to B. Let's connect A with C. And then I am going to adjust the shape of this edge. And again, the shortest way is this edge of weight 31 plus this edge of weight 19 for a total weight of 50. A is connected with C. Let's connect A with D. The weight for this path is 16 plus 16, which is 32. And now we'll connect A with E. And the shortest way is going to be 32 plus 10 for a weight of 42. Okay, now vertex A is connected to every other vertex in the graph. Let's check vertex B. B is connected to C. B is not connected to D, so I'm going to add the edge. The shortest possible route is 15 plus 16 for a weight of 31. B is connected to D. B is not connected to E, so I'm going to add the edge. And the fastest way to get from B to E looks like 31 plus 10 for a minimum weight of 41. Okay, B is now connected to every other vertex. Let's go on to C. C to D. Looks like it's going to be 19 plus 31 for a weight of 50. C is connected to D. Let's connect C with E. And again, I'm going to adjust the shape of this edge. Okay, and then going from C to E, the weight is going to be 50 plus 10 for a total weight of 60. And then connect C with F. And it appears the shortest way between C and F is going to be 19 plus 15, so that should be 34. Okay, and let's see, it appears that C is connected with every other vertex. On to D, D is connected to E and to F. So then the last edge is going to be the edge between E and F. And again, let's see, the shortest way to get from E to F looks like 10 plus 16 for a total weight of 26. Okay, so now I have constructed a complete graph with the Euclidean property. So we're moving on to the next step of the algorithm. So we're going to choose the vertex where the salesman starts. So I'm going to say the salesman starts at vertex A here. Next, we're going to apply the nearest neighbor algorithm. So at each step, we're going to look at the weights of all of the connected edges. We're going to choose the minimum weight edge that travels to a vertex we haven't visited yet. So the minimum weight edge connecting to vertex A is this edge of weight 16 that connects us to F. Next minimum weight is going to be this edge of weight 15 connecting us to vertex B. Next minimum weight edge is this edge of weight 19 that gets us to vertex C. And We have two vertices left that we have not visited. Of these two edges between D and E, the smallest weight is 50, getting us to D. We only have one vertex left to visit that gets us to E. Now we've visited all of the vertices of the graph. We're going to choose the single edge that gets us back to where we started. So we return to vertex A. Next, we're going to apply the deleted vertex algorithm. So this will allow us to compute a lower bound for the practical traveling salesman problem. I'm going to say that I'm going to delete vertex A and all of the incident edges to A. Now, at this step, we're going to find a minimum spanning tree for the subgraph that remains. In this case, we're going to apply Kruskal's algorithm. So we're going to, at each step, choose the edge of minimum weight so that we do not create a cycle. And it looks like I made an error. I thought it was 15. 15 is not the smallest available weight. Smallest weight here is this edge of weight 10. Now I think I can choose 15, and I can choose 16. And we're going to do this until all of the vertices of the graph have been connected. We have one vertex left, so I'm going to choose this edge of weight 19. And then finally, we're going to add back all of the deleted edges and add back the two edges that have the smallest weight. So the first smallest weight is this edge of weight 16. And then the next smallest weight looks to be 31. So this edge here. Okay. So there we have completed the algorithm. And the first phase of the algorithm, we computed an upper bound of 152. And applying the deleted vertex algorithm, we found a lower bound of 107. And that is how you solve the practical traveling salesman problem.